Let's now have a brief recap of the statistics of linear SDEs by using the results from this lecture. So, a general time-varying linear stochastic differential equation has this form. So we have that dx is equal to matrix F times x times dt, and the matrix F is also allowed to depend on time. Then the next term is u function of t times dt plus L, which is a function of t times d beta. And the initial conditions are typically assumed to be Gaussian, with certain mean m0 and covariance p0 given at t0. Using the results from this lecture, we see that the mean and covariance equations are now given as follows. The time derivative of mean m is equal to f times m plus u. And the time derivative of p, the covariance, is equal to f times p plus p times f transpose plus L times q times L transpose. So this is exactly the same solution that we obtained already before. And we can even solve these equations, and the general solutions have this form. So m of t is equal to the transition matrix times m of t0 plus the integral of transition matrix times u. And this is also the solution that we already have seen before. The covariance solution is p of t is equal to the transition matrix times p at t0 times the transition matrix transpose plus then an integral involving the transition matrix LQ, L transpose, and the transpose of the transition matrix. In linear time invariant case, we have an equation dx is equal to f times x dt plus L times d beta, where we assume that f and L are independent of time. Similarly, we get the differential equations, so the time derivative of mean is equal to f times the mean, and the time derivative of covariance is equal to f times the covariance plus covariance times f transpose plus LQ L transpose. And the explicit solutions are exactly the same, except that we don't have u there anymore, and the transition matrix is replaced with the matrix exponential. And we saw these results already before. This linear time invariant case is very important in the applications, and for that reason it deserves some separate treatment. So we will notice that the mean equation is quite simply solved using the matrix exponential function given here. But the covariance equation still involves the integral, so that it's not explicit representation of the solution in the sense that we have for the mean. But in that, what helps us is something called matrix fractions method. So it turns out that even though the covariance differential equation is not simple linear, we can form two linear differential equations, which as a joint solution will give us the solution to the covariance differential equation completely. So let matrices CT and DT solve the linear time invariant differential equation of this form. So the time derivatives of C and D are equal to matrix F LQ L transpose 0 minus F transpose times the C and D joint matrix. Then P of T, which is equal to C of T times the inverse of D, solves the differential equation of the exactly the same form that we had for P. Thus, it turns out that we can actually solve the covariance with the matrix exponential like this, and then we can just substitute these C and D that we get to the equation of P here. Let's now take a look at the Markov properties and the transition densities of stochastic differential equations. So a Markov process is defined to be a process such that the property density of x of t given the history of the process up to time s is equal to the property density of x of t only given the last value of the history x at s. And it turns out that all Ito processes are actually Markov processes. And the property density x of t given x of s is called the transition density of the process. And it also defines the statistics of the process completely. The transition density is actually also a solution to the Fokker-Planck-Kolmogorov equation. We just need to set the initial condition of the Fokker-Planck-Kolmogorov equation to correspond to starting from x at s. all the finite dimensional distributions, that is the distributions of any finite subset of times of x, can be written in terms of the transition density. So the joint distribution of x t0, t1 up to tn is equal to the probability density of x t0 times the transition densities from I-1 to I, where I goes from 1 to n. In the LTI case, we can actually write down the transition densities in basically closed form. In almost closed form, because we might have matrix exponentials that don't have explicit representation, but we also know that it's very simple to compute matrix exponentials using software such as MATLAB. Let's take a look at the solution to a linear time invariant SDE. So the solution, as we saw, is that the mean is given by the matrix exponential of f times t minus s times m at s, and the covariance is given by matrix exponential of f times t minus s times the covariance at s times the matrix exponential transposed plus the integral of the matrix exponential L, Q, L transpose and the matrix exponential transposed. And now the transition density actually corresponds to conditioning the mean and covariance on the value of x at s, which corresponds to setting mean of s to be exactly equal to x of s and setting covariance formally to 0. So these will be the initial conditions at time s. The transition density then turns out to be a normal distribution with mean given by matrix exponential of f times t minus s times x at s, and the covariance, the integral of matrix exponential times L, Q, L transpose, and the matrix exponential. And this integral term is actually exactly the second term in the solution to the covariance differential equation. In the linear time invariant case, we can actually write down the transition density x tk plus 1 given x tk as follows. So we can define the delta tk as tk plus 1 minus tk. Then the transition density is given, it's a normal distribution where the mean is given as a matrix exponential of f times delta tk times x at tk, and the covariance is given by integral from 0 to delta tk of matrix exponential L, Q, L transpose and the matrix exponential. The integration is not from tk to tk plus 1, but from 0 to delta tk because the system is time invariant. But now we can see the system as being weakly equivalent to a discrete time system of this form. So we have a x at tk plus 1 is equal to a matrix times x at tk plus qk, where this qk is some kind of Gaussian zero mean random variable. And we can actually recover this a to be equal to the matrix exponential of f times delta tk, and the covariance sigma is equal to the integral from 0 to delta tk of the matrix exponential LQL transpose and the matrix exponential transposed. So this discrete time is weakly equivalent to the original SDE in the sense that the finite dimensional distributions are the same at times tk, where k runs from 1 to big K, say. These kind of equivalent discrete time representations are extremely useful in optimal filtering theory. So usually, or quite often, we have a continuous time system that we sample or measure at a discrete time instance. Then it's useful to solve the dynamic model stochastic differential equation at the measurement points and then only consider those points instead of the values between. So for example, the Wiener velocity model is very simple and commonly used model to model dynamics of various dynamic systems. So it says that the second time derivative of x is equal to a white noise. And in more rigorous Ito SDE form, we can write it down as, so the differential of vector x1, x2 is equal to matrix 0, 1, 0, 0 times the vector of x1, x2 dt plus then matrix 0, 1 times d beta. And now we can write down the matrix A and matrix sigma for this model. So A matrix is simple because it turns out that the second power of the matrix is 0. So we can write down the matrix exponential in closed form just by using the first two terms in the Taylor series of it. And the sigma matrix turns out to have this kind of form. So actually, we could also compute the sigma matrix quite easily using the matrix fractions. So in that case, we wouldn't need to integrate anything, but we could numerically just use the MATLAB's matrix exponentiation routine to compute it. So let's then summarize what we have learned during this lecture. The probability density of an SDE solution solves something called Fokker-Planck-Kolmogorov partial differential equation. The mean and covariance of the solution in turn solve a pair of ordinary differential equations. In nonlinear case, the expectations in the mean and covariance differential equations cannot be solved without knowing the solution to the Fokker-Planck-Kolmogorov equations, so they are not practical in that sense. For higher order moments, we can derive theoretical differential equations as well, and we can approximate them with moment closure. We also saw that the stochastic differential equations are Markov processes, and they can be characterized via transition densities. For linear stochastic differential equations, we can solve probability densities, mean and covariance equations, and the transition densities, as well as all moments explicitly.